Force on a current carrying wire. A thin 1.4 meter long aluminum wire carrying a current to the right has a mass of 0.12 kilograms and is suspended above the ground by a magnetic force due to a uniform magnetic field of 2.2 Tesla. So we got four parts here. A, on the diagram, show all the applied forces on the wire. B, what is the net force on the wire if it is in equilibrium? C, on the diagram above, show the direction of the magnetic field. And finally, D, what is the magnitude of the current flowing through the wire? All objects that are at least near Earth experience the force of gravity, which is directed towards the surface. So we draw the first force here, right? The wire is being pulled down by gravity. But the key word in this problem is suspended. This means that the wire is stationary and its acceleration is zero. The force of gravity is balanced by another force, which is applied by the magnetic field. So we call this force here the magnetic field force F sub B. And note how they're both equal because the wire is not moving. This is almost a trick question. You're being asked for the net force. So you might see force, you see a current, you see a magnetic field, you see a length. You might automatically just start going ahead and calculating it. But please don't do that. It's net force. Based on our information, the wire is stationary. It's not moving, so its acceleration is zero. So when we apply Newton's second law, the sum of the forces, or the net force, is equal to ma is equal to zero, so the net force on the wire is zero. Now we need to show the direction of the magnetic field. So we're going to use the right-hand rule kind of backwards. We're going to start, and actually this isn't the backwards part, you point the four fingers of your right hand in the direction of the current, and that's to the right. Now, instead of facing your palm towards a magnetic field, you're going, because you don't know which direction the magnetic field is, you extend your thumb perpendicular to your fingers, pointing in the direction of the magnetic force, which is to the top. We showed that on the previous couple slides. So we have our thumb pointing up and our four fingers pointing to the right. So now curl your fingers perpendicular to your palm, or just look where your palm is facing. That will show the direction of the magnetic field, and that is facing into the page. And again, another caution at the bottom. The question asks about the external magnetic field. It did not ask you for the magnetic field generated by the current carrying wire. So please don't make that mistake, because you might have done this. Here's the wire and the magnetic field. You do the right-hand grip rule, put your thumb in the direction of the current, and you find that the magnetic field below the wire is into the page and above the wire is out of the page as it circles the current carrying wire. But that's not what's being asked for. We're looking for the external magnetic field. First, solve the magnetic force on the wire using Newton's second law. Then use the equation for the magnetic force on a current carrying wire and solve it for the current. So here's the Newton's second law. Sum of the forces is equal to ma. And from our free body diagram a few slides back, we have the magnetic force in the up direction, so we give that a positive sign. Mg in the down, negative. It's not moving, so the acceleration is zero. So the magnetic force is just mg. Substitute in our givens, and we get 1.18 newtons. Now we use our magnetic force equation right here. It's Philb. F is equal to ILB. We divide both sides by L and B to isolate the current. We put in our magnetic force that was calculated here. Divide through by L in the magnetic field, and we get 0.38 amps.